Hello and welcome to Projectile Motion's Harder Problems, video 1.2 for physics. In this video I'm going to run through how to do 3 of the more difficult problems about projectile motion. Let's start with this one. A ball is thrown horizontally at 22.2 meters per second from the roof of a building, and it lands 36 meters from the base of the building. How tall is the building? Well, as is always the case in these, we should start by drawing a picture. Here's our building. We actually want to know how tall that is, so I'm going to call that Y. We know that it was launched horizontally at 22.2 meters per second, and that it lands downrange at 36 meters. So in order to find out how tall the building is, we first need to find out the time it takes to do the fall. So we know that the velocity in the x direction is a constant, and that is our range over our time. So we can start with that equation. We can then say that time is then our range over our x velocity. So the time it takes to do this path is 36.0 over 22.2, which, if we calculate that out, turns out to be 1.62 seconds. So that's how long it takes for our ball to follow along this path. You can always find the time first if you know the range. Otherwise, you'll have to find the time by using the vertical distance and keeping in mind that we have acceleration there. All right, so the second part of it is how tall is the building? So we want to know what is y. How tall is the building? Well, we can use the equation that y is equal to Vy naught t plus 1/2 at squared. Y being the height, we get to determine where the origin of the system is. We can say that the origin is up here at the ball, and then y will be a negative number. Or we can say that the origin is down here at the ground, and y will be a positive number. It's up to you. It doesn't really matter. We can also say that the origin is where we throw the ball from, and downward is a positive direction. You choose, just be consistent throughout the problem. So if I am going to start with this equation, the initial velocity in the y direction is 0 because it is thrown horizontally. So I can cross out that term completely. So then y is equal to 1/2 at squared. Keeping in mind that the acceleration of this ball is going to be gravity, we can quickly determine y as being 1/2 times 9.8. I'm going to call that a negative, times my time, 1.62 squared. And again, the negative 9.8, it's negative because I like to keep with my upwards being positive, downwards being negative. So this will end up giving me a negative y, but that's okay. I multiply those together, and I find out that the ball has to drop 12.9 meters. You can't have a building that's negative 12.9 meters tall, so the final answer would be 12.9 meters. So again, the first thing you have to do is find the time, keeping in mind that horizontal speeds are constant. Then you pick one of your other kinematics equations, apply it to projectile motion, and solve for the height. Let's look at another one. A projectile is shot from the edge of a cliff 125 meters above the ground level with an initial speed of 65 meters per second at an angle of 37 degrees with the horizontal. We have 2 things to determine to begin with here. One is to determine the time taken by the projectile to hit the point P at ground level. The second is to determine the range of the projectile as measured from the base of the cliff. So to start with, let's write down what it is we know. Well, luckily we've been given a diagram here, so we know the initial velocity is 65 meters per second. We know the initial angle is 37 degrees. We know the height is 125 meters. So now we just have to add in a couple of other things. We know that acceleration is equal to gravity, and because it is in the downward direction, we know then that we're going to call it negative 9.8 meters per second squared. So then we need to figure out where is our origin and what are we going to use for figuring out the time taken. Well, we can certainly start with the fact that let's have the origin up here. Let's have the origin here at ground, okay? And up is positive. And if that then is the case, then we want to know the time. We have the height here, so we know that we're probably going to use the y equals v naught t plus 1/2 at squared. In order to use that, we need to figure out what is the initial velocity in the y direction. So the velocity initially in the y direction is going to be, well, let's look over here back at the picture. The y component is going to be the sine. So it is v naught sine theta, which in this case is 65 sine 37 degrees. 65 sine 37 degrees is 39.1 meters per second. So now that we have the velocity in the y direction, we can use that to figure out what is our time taken for this to occur, because the final height that we will be at will be 0. So if we go back to our y equation, remember that it's really y equals y naught plus vy naught t plus 1/2 at squared. Our final y is going to be 0. Our initial y is 125. Our v naught is 39.1. T plus 1/2 at squared. Remember that a is 9.8, and it's going to be a negative 9.8 because it's going downwards. So it would really be minus 9.8 over 2 t squared. If we rearrange this equation to solve for t, keeping in mind that this is a quadratic, so we're going to use a quadratic equation, which is that t is equal to a negative b, so a negative 39.1 plus or minus the square root of b squared minus 4 times a for AC all over 2a Now notice that I rearranged the equation before I bothered to simplify 9.8 over 2 or anything else. Typically, you can either plug the numbers in, simplify, and then solve, or you can do the algebra to rearrange the formula and then plug the numbers in afterwards. I prefer to actually plug the numbers in later. I just didn't do it this time for some reason. If I solve for t here then, I end up with two answers, of course. One being that t is 10.4 seconds. The other one is a negative 2.45 seconds. We can't have negative 2.45 seconds for time, so the answer to part A is that it will take 10.4 seconds for the object to land at point P. So for part B now, we are asked to determine the range of the projectile. Well, the range is determined by the velocity in the x direction. So keeping that in mind, similar to the problem before, our range is going to be the velocity in the x direction times time. Velocity in the x direction is going to be v naught cosine theta times t, which will be 65 cosine 37 times 10.4. We do that out and we find out that this projectile has a range of 541 meters. So it actually travels quite a ways there on the across the plains or across the valley. So again, look for components, figure out time, then go ahead and solve from there. This problem continues, however. At the instant just before the projectile hits P, let's find the horizontal and vertical components of its velocity, the magnitude of its velocity, and then finally, let's figure out what the maximum height above the cliff is that's reached by this projectile. Well, right before, if we look at part C, right before this hits the ground, its x component of the velocity is going to remain the same as it did before. So for part C here, velocity in the x is a constant, we know that. And we had solved that on the other side, or at least we had looked at it on the other side, because remember it is v naught cosine theta. We can plug in v naught being 65, cosine 37, that is 51.9 meters per second. This is Vx. All right, so now we need to find Vy, but we had found that already, right? If we go back here and take a look for a minute, at the very beginning, we found the original Vy to be 39.1 meters per second, and that's going to be important because now we have to go back and say Vy final is equal to Vy initial plus AT using another one of the kinematics equations. Remember, like I just said, Vy initial is 39.1. AT is going to be a negative 9.8 times T of 10.4. And we find out that right before it hits the ground, our final velocity in the y direction is a negative 63.1 meters per second. Remember, the velocity in the y direction is negative because it's falling now at this point. So Vyx is a constant 51.9 meters per second. Vx is a constant 51.9 meters per second. Vy has changed from being a positive 39.1 meters per second to being a negative 63.1 meters per second. So in order to find part D, the magnitude of the velocity is basically looking for the overall final velocity right before it hits the ground. Well, we've got a y velocity coming down, we've got an x velocity going over, so we can find their resultant velocity by doing Pythagorean theorem. So the final velocity is equal to, final velocity squared is equal to the x velocity squared plus the y velocity squared. So the final velocity is the square root of 51.9 squared plus negative 63.1 squared, which turns out to be 81.7 meters per second. All right. This last part's a little bit more complicated because you have to take into account what's happening at the very beginning. Remember that if we look back at the picture, it was at the cliff, but it was going up first. So the question here is, what is this distance? What's the maximum distance above the cliff that the ball gets to? How high did it go before it started coming down again? To figure that out, we need to think about what happens at the maximum height. Well, we know at the maximum height, the velocity in the y direction is going to be 0. The velocity in the x direction is a constant, it does not change, but the velocity in the y direction is going to be 0. We don't know what time it reaches the maximum height at, so we do not want to use an equation with time in it, but we do know the acceleration. We know its original y velocity. We know it's going to start, if we take the cliff to be our 0 point, we know it's going to start at a height of 0, and we want to know its maximum height. So this looks like it would be a great use of vy squared equals vy naught squared plus 2a y minus y naught. At the top, again, at the top of its maximum height, the velocity is going to be 0. If we say that the top of the cliff is a 0 point, then we can go ahead and figure out from there how much higher we go. And so we're looking for y. So if I solve this equation for y, then y is equal to vy naught squared over 2g, because remember the acceleration is a negative 9.8 because it's still accelerating downward even though it's going upwards. Plug in my numbers here. The initial y velocity is 63.1 squared divided by 2 times 9.8. I find out that above the cliff, the maximum height above the cliff level is 78.1 meters. So even though it doesn't appear in the picture that the ball went all that far above the cliff before it started to go down, the total cliff was only 125 meters tall, but before the ball starts to come down, it travels more than half that distance again high. So it goes 78.1 meters above the cliff first. Now, one last thing to make sure that you understand why I chose the cliff height to be 0 here. It's because we are asked what is the maximum height above the cliff. If we were just asked what is the maximum height reached by the projectile, we would not be able to make y naught equal 0. All right, one last problem here. And then you should have enough information to solve some harder projectile motion problems. When Babe Ruth hit a homer over a 7.5 meter high right field fence, 95 meters from home plate, roughly what was the minimum speed of the ball when it left the bat? Assume the ball was hit 1.0 meters above the ground and its path initially made a 38-degree angle with the ground. Okay, so again, first thing we got to do is draw a picture. Make sure we know what the heck's going on here. We have Babe Ruth over here. He's going to hit a ball. It's going to go like that. It is, the wall is here. And we know that the height of the wall is 7.5 meters. We know that it started out at a height of 1 meter. We know that the wall is 95 meters away. And we know that the angle of the hit is 38 degrees. What is it that we're looking for here? Let's go back. What is the minimum speed of the ball? So we are looking for the initial velocity. When we're looking for the initial velocity, again, it's projectile motion. We have to keep in mind a few things. First of all, we want to keep in mind that we know that the range is determined by the x velocity times time. And we know that the x velocity does not change. We also know that the x velocity is simply the initial velocity times the cosine of theta. I'm not interested in the x velocity at all. I am interested in the initial velocity. So, as is true all the time, we need to know something about time in order to be able to solve this problem. The question then becomes, well, if delta x equals v naught cosine theta t, what is t equal to? So if I rearrange this equation for t, I get delta x over v naught cosine theta. So this gives me an expression for time. I'm not going to put numbers in yet, and I really can't because I don't know v naught yet. But I also know that if I am looking for the vertical motion, then I need to use the equation that tells me about the y's. So I'm going to start with this equation. I'm going to leave it there for just a minute, and I'm going to say, all right, so this tells me about the range, but if I want to look at the y, the final y, or the final height that the ball goes, is equal to the initial height plus vy naught t plus 1/2 at squared. And again, I'm going to rearrange this slightly because y naught is fine, y is fine, but my vy naught is actually v naught sine theta t, and my 1/2 at squared is really minus 1/2 gt squared. So now I have these two equations. I have an equation for t and I have an equation for y. I'm interested in v naught. I could certainly at this point take my t equation and substitute it into both the t and the t squared equation. However, that turns into a mess because you end up having the velocity, the initial velocity, in the denominator of a squared term. And that makes it ugly math to solve. So what I'm going to do instead is a little trick where I only substitute the t into the first of the t's. And I'm going to then solve for the other t. It still works out the same. You still mathematically get the same answer, but it's not as messy. So I am not going to do substitution into the second one. I am, however, going to substitute into the first one. So substituting it in, this equation becomes y equals y naught plus v naught sine theta times delta x over v naught cosine theta minus 1/2 gt squared. And again, you may say, but wait a minute, I'm looking for the initial speed, so why am I putting velocities in there that are going to cancel each other out? And the reason for that is because it then makes our life easier, and we can come up with time, and then we can substitute in back into our time equation, back into our original delta x equation, and come up with the speed. So the v naughts cancel, and we can then rearrange this equation to solve for t, and t then equals the square root of 2 times y naught minus y plus delta x tan theta. Okay, subbing in some numbers. Oh, sorry, I forgot the over g. Subbing in our numbers, we get the square root of 2 times y naught is the initial height, which is 1, minus the final height of 7.5, plus delta x of 95 times the tan of 38, all over 9.8. We solve that for time, and we end up with 3.718 seconds. So we have time. A little bit convoluted way to do it, but again, we start with our range equation of range is equal to vxt. We solve that for t. We then put that into our height equation of y equals y naught plus v naught sine theta t minus 1/2 gt squared. We only substitute the t into the first of the t's in that y equation. We rearrange, solve for t, and we find out that it takes 3.718 seconds. We go back to our range equation here, and we say, okay, delta x is equal to v naught cosine theta t. So v naught is equal to delta x over cosine theta times t, which is 95 over 3.718 times the cosine of 38, which gives us an initial velocity of 32 meters per second. So Babe Ruth had to have hit the ball with a speed of at least 32 meters per second in order for it to go over the 7.5 meter high right field fence. Take a minute, go through the problems here another time or two if you need to, and they should give you the information you need to continue to solve some more difficult projectile motion problems. Bye for now.